In water also people have found fans, but mainly for water. Actually was
the grains.
But all
Grains.
process industrial problem, all the responsibility.
yeah. It is the thing which we would not like is this, we want to mix properly, and this rotation called demix. So a lot of people are trying to solve this. Still a very simple explanation.
What was the content of the
Sand of two sizes, and one had been colored dark. So yeah, roughly same.
It would be different.
Yeah, we just pour it. So this is an experimental delay because it can go on varying diameter of the tube, length, the size ratios, and the proportions of the sand, speed of rotation. One subtle thing you notice while doing this, see the way it's designed, it moves axially also. So you have to hold your hands while turning it. Otherwise, that axial movement will disrupt some of the fan formation. Another one is Mr. Raghuram's suggestion. See, when we had it in the lab with this handle, people will go on fiddling with it, whoever is passing by, and they'll break this tube. So he now has a removable handle. So leave it alone.
The problem was originally it was longer. When I keep it, everybody makes two rotations, drags them. And I thought remove the handle so that nobody will rotate.
preventing experiment?
Everybody will make two rounds, go again another, finally one further break. And it was more length up to this. So the 4 inches was reduced. Because the handle kept to rotate.
This is an interesting one. Program just hold this one. So again, it is timing. If you don't want anybody else to come. See, I'm just using it. Don't they will time it just somewhere close. Is it ready or some? Oh no, don't. Okay, doesn't matter. Now I'll say 1, 2, 3. So this is just a funnel connected to tube. Yeah, take your time. So when the last grain of sand is present, you certainly take this because some sand.
Takes two time, so long time, huh? 25 o'clock.
But if anybody, okay, he's ready. I'll say 3 and till it 1, 2, 3. Okay, please note that time. You want me to do it again? Now we'll do it this way.
Just hold on.
We just hold it. Yeah. Where do we? Yeah? Okay, now again we ready. You will yeah. Just don't remove it. Yes.
Count
Yeah.
three. Count three.
Yeah, yeah. Don't remove. Just be ready. No, no. Okay. All right. Yeah. 1, 2, 3. This one usually works now. Okay. Time. Hopper is just a funnel. How much was it?
7.7.
7.77.
2.4.
2.4. So at least 3 times faster, same mass. So the question is, why is the flow rate more?
Normal reaction.
Yes?
In the funnel,
Yeah.
there was always a normal reaction acting upwards. But I think in this vertical, only till the upper the sand was in this funnel now, then only the effective normal reaction was acting.
Yes.
As soon as it came, then only the normal reaction, because of friction, was acting in opposite direction.
Okay. So no, the same funnel, dimensions are there in this one and this one. Same funnel.
No, I'm saying when the sand was in the circular part, now it's a tube part.
Yeah.
Then there was not any normal reaction on the upward direction directly.
Fine. Suppose we take that for granted. In the upper part is same as this.
Yeah.
Huh?
Less amount.
I can add more, still it won't matter. Hmm? So any other explanation? A good attempt, but just something to do with this junction. This one is difficult to answer.
Yeah, you cannot even remove the head being different. Because somehow like it blocks there and vertically it just goes down. Jam.
The vertical it flows much faster.
At that juncture.
The flow pattern is different.
Yeah, actually it's maybe difficult for us to imagine. The interaction with the interstitial air is the cause for all this. Okay, so people have measured pressure at this junction that is flowing, and the top and bottom are open to atmosphere. So there is actually vacuum is formed. So because the vacuum is formed, the pressure is high at the top and low here at the junction between the funnel and the pipe. So there is a favorable pressure gradient acting, high pressure on top and low pressure here, which actually drags the particle down. So the hopper, it discharges much faster than if you had only this. I think I forgot to bring the pressure profiles, but yeah.
The lower portion is like the atmospheric pressure as well.
The bottom, yeah. Right.
There is a vacuum over there.
Yes,
So shouldn't we try to move upwards as well?
Okay, there is. Let's call that y, and we plot pressure here. So let me start from higher. From here. So at the top pressure is atmospheric, and it falls. This is positive, so it falls. Okay, draw it here. Sorry. It goes to negative value at this point, vacuum, then comes back to atmospheric at the bottom of it. So the pressure gradient is changing sign. But the crucial one is the one in the hopper. In the pipe, if you observe, the flow is very dilute, and the major resistance flow is this one. So this is where this pressure gradient drags the particle down and helps it discharge much faster. So in the industry, it is used to deliver catalyst particles against adverse pressure gradients. That is, you can have, let's say, PA here, and you can have PB greater than PA. And up to some limited range, it will still flow down the particles. Okay? So if you plot the flow rate, mass flow rate of particles, dimension that in some way, versus the pressure rise, PB minus PA. Then what we'll expect is, as the pressure rise increases, the flow rate will decrease. So we'll get one branch like this. But curiously, because of the form, the drag relation, and the non-linearities in that, you get a second branch like this. And the third branch, we cannot determine experimentally easily, but models for this one-dimensional model, we show third branch. Stability analysis has been done. These two are stable as you might expect, and these are unstable. So if you come this way and increase the pressure rise, the flow rate decreases like this, suddenly jumps down to this value. If you go backwards, it will jump up. Now this is scale with respect to the bare hopper, which are the flow rate somewhere. So the upper branch, the flow rate is more than the funnel. The lower branch is less. So these kind of things have been analyzed, and people in industry were interested in this. Catalyst part, cracking catalyst. Yeah.
Why does the vacuum form there?
Why does it form there? See, both top and bottom is atmosphere, and in the pipe, the particles are falling down faster than the gas. So relative to the particles, the gas is flowing up. So if the pressure is atmospheric, pressure will be lower than at the junction. Then because the top is atmospheric, it has to go.
So length of the pipe will change anything?
Yeah, if you make it very long, gas compressibility becomes important. So it affects the extent of energy. I don't know all the details, but people have looked at length of pipe. If you have coarse powder, the effect is not so dramatic because the gas can easily permeate the powder. The permeability is strong function of particle. So only in fine powder you will see this pronounced effect. I think I should now finish. Okay, this experiment. Yeah. So instead of sand, it's water. Water also some enhancement will be there, but not so. That is the pressure at the junction will become below. But in the water, the flow in vertical depends on the head. Whereas this one not much head.
Because of this pipe,
Correct.
pressure becomes zero.
Right. Less than. Yeah. This is just a tube with an orifice at the bottom. So it is filled with the powder, silica gel. You can hear the sound now. Below some height, you will see it will stop. See if you measure the flow rate now and before, almost the same, but there is no sound. So this kind of sound is called silo music. For the big silos, it used to be very loud and disturb people in the surroundings. Yeah, this is the orifice, just the whole. Now if you do the same experiment but incline the tube, beyond a certain angle again there is no sound. Here what happens is, you can't see it in this tube. Air bubbles tend to enter in the upper part of the tube and travel up, somehow that disturbs the sound. So let me say something about these references. For a long time, people were thinking this sound phenomenon was discovered in the 60s and 70s. This is one of the papers, the second one. But one day I went to library to check this tube experiment, the original reference, which was 1910. And I found here, I've done this experiment long ago. So it's always helpful to look at the original reference. You may find some valuable information there, which you won't find in the secondary source. Now we will do this boat experiment. Last one. This is time to cross the tank. This light. Yeah. Yes. No. Matchbook. Yeah, you can come and see if you're not seen it. Some of you might have seen as children. Nowadays they don't sell it so commonly. Used to be sold, nowadays